there, everybody. Welcome to today's webinar. We're going to talk about voltage, current, and resistance. Thank you so much for joining us. As you get settled into the Zoom room, go ahead and navigate to the bottom of your Zoom window. You'll see what looks like a little chat bubble, and I'll encourage you to click that. That's going to pull up the webinar chat. We are going to be answering your questions in today's webinar chat. So make sure if you have any questions during today's presentation, drop them in there. I'm going to have my eye on the chat and I'll answer what I can. And if we surpass my level of knowledge, I'll go ahead and wait for a good pausing point and ask Josh, and I'm sure he'll check in as well. To make sure it's working well for everyone, go ahead and click that chat bubble. And in the comments, go ahead and let me know where, if anywhere, you traveled for Thanksgiving. Let's see if we have any jet setters in the chat. So we've got Atlanta, very nice. Ohio, pretty good, pretty good. I stayed here in Oregon, stayed home and comfortable. Yep, me too, me too. That's awesome. Stayed home and cooked. Yep, us too. We had turkey. I don't know about you all. Northwest Montana, stayed home. Awesome. Some folks saw their family, stayed home. New York, big travel time there. We are about a minute past the hour, so to make the most of our time together today, I just wanted to hop into some quick housekeeping items. And from there, I will pass off the conversation to today's presenter. So the first piece of housekeeping that I wanted to share with you was a reminder that we do want to answer your questions. So just like you're putting questions, comments in that chat bubble, keep putting it in there. We are happy to answer your questions. If we happen to not get to you, please do shoot us an email, give us a call, chat with us on our website. We are here to help. So you can email us at physics@vernier.com. And then there's a lot more contact information on our website for anyone who needs it. The second piece of housekeeping that I wanted to share with you is that you will get a recording of today's webinar. So keep an eye on your inbox. It usually takes us about 3 to 5 business days to get that video edited and put it online. But as soon as it's ready, you're going to get that recording. In that email, you're also going to get a resources folder that has today's presentation, along with a certificate of attendance and some experiment files that Josh is sharing with you. I'm going to pop that in the chat just now, and then if you need it again, please feel free to ask. I will be here the whole time, so put questions in the chat. We'll keep an eye in there. And with that being said, I'll pass you all off to Josh. Thank you so much.
Thanks, Dylan. I'm looking forward to talking to you all today about simple circuits and how you might, some lessons that you might use with your students to teach simple circuits. We'll do some quick introductions first. I'll introduce myself. I want to get to know you a little bit better. I want to talk a little bit about when it goes to teaching like simple circuits, kind of like the tools that we're going to use, some of like the core ideas that you would usually want your students to learn when you teach simple circuits. And I have a sequence of 4 labs here that I want to go through, and I want to go talk about some of the details of each. As Dylan mentioned, I really want to make sure that this webinar is useful to you. So if you have questions, please post them in the chat. We'll have time at the end to answer questions. And if Dylan will interrupt me for pertinent ones as well. Let's talk. Dylan's going to put up a quick survey here. I want to know a little bit about how much you know about Vernier technology already, what grade level you teach. That'll help me better tailor my comments here to where you might be. While you're answering those questions, I guess a quick introduction for myself. My name's Josh. I've worked for Vernier for about 10 years now. Prior to Vernier, I was a high school physics and engineering teacher in Northern Virginia. I taught for 10 years there, had a great experience. I used Vernier products in my classroom, and I found I really loved hands-on science education. The hands-on part was really important. Here at Vernier, I do a lot of customer service type stuff, a lot of tech support things, like if you call or email with questions or concerns, broken equipment, that sort of thing. I'm one of the folks that might answer those questions. And then I help with product development. I go to science teacher conferences and I do webinars like this. It's really a great thing. It looks like everybody already has some Vernier stuff and is using it. Some folks are very comfortable. Some are still on that learning curve. That's great. I hope that you find something useful here. And it looks like we don't have any middle school teachers. We've got mostly high school and some college instructors. That's great. The lab sequence I'm going to show today is perfect for high school and beginning college. You know, when you are the first time students really do like a quantitative dive into simple circuits. What we're going to do today is great for that. Let me talk a little bit about the tools that I'm going to use today and what your options are as far as these labs go. So we make, when it comes to actually building the simple circuits themselves, you have things like most folks use kind of like batteries and bulbs. That's what I've got. That's actually what I'm going to use today. Something like these, actually these guys here on the right. I really like these battery holders because they clip together. They like slide together. You don't have to use another alligator clip for those. And then these little round, just single E10 bulb holders. They're also work really well with alligator clips, and they're so simple and so inexpensive that when kids inevitably crush them and deform them, you can just use another one. At Vernier, we do make a circuit board. This has got all the components and place for batteries and that sort of thing all built together. This is really great for kind of like an all-in-one solution. You can, everything you need there, you can just whip out, you just attach the alligator clips to create your circuits. It's definitely better for college students or second-year students just because the circuits that you build on the circuit board aren't going to necessarily look like the circuit diagrams that students see in their labs and textbooks and stuff like that. Moving from a circuit diagram to how that looks on the circuit board takes some practice. And so definitely batteries and bulbs tend to be easier for those first-year students. Once if you really want lots of stuff, make the most of your money, the circuit boards are great. If you got AP students or second-year students, it's also the circuit board is wonderful. That's how you're going to build your circuits, and then you're going to want to measure things about your circuits. And we make a voltage probe and a current probe that you use with our software. That's what I'm going to use today. But for most of the labs I'm going to show today, the digital multimeter or just an old school analog ammeter, voltmeter, those will work just as fine as well. We aren't going to do anything today that requires measuring like voltage or current versus time, and so the logging isn't as necessary. And so like a multimeter or an ammeter, voltmeter, analog ammeter, voltmeter will work just fine. I would still recommend the voltage current probes in the software simply because you very quickly get to points where you do want to measure, say, voltage versus time if you're going to do like an RC circuit or an RLC circuit, and you want to be able to measure those sorts of things. Those analog or the digital multimeters, they're not going to work for you, and it really is great to have those tools. Carrie, I know you asked a question here about whether there's a good place to find these E10 bulbs. So if there's an easy place, we sell them. I don't know that I would recommend buying them from us unless you're buying other stuff as well, just because they're so inexpensive. The shipping feels like you're paying more for shipping than you are for the bulbs themselves. You can get them off of Amazon, and there are a couple of other websites that sell. My experience with buying them from various websites is that the quality, they're really cheap, but the quality tends to be pretty mixed bag. Like out of the 100 that you buy, you might find 5 or 6 that right out of the box are duds. I suspect that's just kind of par for the course these days. Yeah, I agree. Often, like when they might arrive broken, just crushed even, like if they haven't been packaged well. I know that they won't if you buy them from us, but that's, like I said, unless you're buying other stuff from us, it's probably not the best. And thanks for that suggestion, Fred. McMaster Car, we use McMaster Car for lots of things. I don't know that I've ever used Mini Science, but I'll have to check that out. The activities I'm going to do today are I've dropped PDFs of the student instructions and the teacher notes into the Google Drive folder that Dylan shared with you a minute ago. These 4 labs, 3 of them come from our lab book, Physics Explorations and Projects. This is kind of a guided inquiry book, of physics labs. The last one, Ohm's Law, comes from just our regular Physics with Vernier lab book. The sequence that I've suggested here is, it builds on itself real well. The very first one is a great introductory activity. It's just about how do you measure electric current in a circuit. How do you use an ammeter? You have students who are just going to get positive and negative values, and it gives them get opportunity to talk about what does that mean. It has students look at series and parallel connections. They kind of understand the difference between those. The second activity is called conservation of charge, and it's really students kind of build the idea of the junction rule, the idea that all the current flowing into a junction in a circuit is equal to the current flowing out of it. The third one is voltage in a circuit, and it's Kirchhoff's loop rule, the idea that as you move through any closed circuit any closed loop in a circuit, the sum of the increases and decreases of the electric potential should add up to 0. And then the last one then is Ohm's law. It's usually, often you start off with Ohm's law, but you actually don't need Ohm's law for any of the preceding activities. And if you want, you can put Ohm's law anywhere in there after that first one. But I find that it tends to work best once you get to the end. By that point, students have a pretty good idea of electric current and voltage, an idea of how those things work together. And Ohm's law kind of ties it all together in a nice, neat package. So I'm going to talk about these labs individually, and I'm going to do that. I'm going to switch a little bit back and forth between my slides here, and then I have some circuits set up here, and I'll show you kind of how I use graphical analysis and my probes to make measurements on those circuits. So the first one is measuring electric current, and I find that a lot of folks, they hesitate to do real hands-on circuit labs with their students. They're great labs. They're very engaging. The math isn't very hard, so they're popular. The problem is, it seems like you go through a lot of bulbs, you go through a lot of batteries, and it feels like it's a lot of consumables that you're using there. And we had a college professor that did a sabbatical with us for a year, Keith. He was great. And he encountered this problem every year with his physics students, and he came up with this lab setup that really works well. The idea is that you create a circuit for your students. You say, okay, you're going to put this circuit together, and there are certain parts of the circuit that students are not allowed to touch. There's a test probe that's measuring the current in the circuit, and there's a test bulb. So there's one of these bulbs, and students aren't allowed to touch those. The other part of the circuit, these 2 other bulbs here, they can do whatever they want with those, And in this lab, you show students, you set up this circuit, and you show students that I can measure a single bulb. If I just connect one bulb in a loop here with my battery, I can measure the current very easily. But how would I measure the current if I have more than one light bulb? And so you add in 2 more bulbs, and then you challenge them and say, okay, my current probe, I'm not going to touch that. My test bulb, I'm not going to test that. And I'll know that if I take my second ammeter here that I'm going to use to measure bulb 1 or bulb 2, if I do something to my circuit that changes the current reading, or brightens or dims or cancels out my test bulb, then I know I'm probably not measuring what I want to measure. And So it's a great way, but because they can't change that, they can't touch the test bulb, and they can't touch the current bulb. If they short circuit bulb 1 or bulb 2, or we still have enough resistance in the system that you're not burning out bulbs, you're not running your batteries dry, and it really works well. So I'm gonna switch scenes here. I'm gonna show you a little bit what this looks like. I have these little bulbs, and I'm hoping that the camera picks it up well enough. So I'm going to switch here to my other screen. This is, I've got a camera pointed down here. I'll move graphical analysis out of the way. I've got my bulbs here in a simple circuit. And if you were to do this activity with students, typically what you would do is you would just say, okay, I'm going to start off with just one bulb. I've got my batteries, I've got my current, so my voltage probe, and I'm just going to connect one bulb in here, and that's going to light up. And I know that my current probe is going, oh, doing the wrong way here. I'm not thinking about what I'm doing. I know that my current probe is just going to measure the current through my single light bulb, because that's the only option I've got. That's the only thing it could be measuring. And let's see, is that enough? There we go. You can see it's shining. Keep that one on. And then you challenge your students. Okay, what if I have 3 bulbs though? Now I've got bulb 1 here. It's connected to bulb 2, and then bulb 2 is connected to my test bulb. And now I can see all 3 of them are lit. How do I measure the current that's flowing through this one, the current that's flowing through this one, without affecting the circuit, without changing things? I'll know things have changed because my current reading is going to change, or my test bulb might get brighter or dimmer. One thing I've done here that you might not be able to see is I actually have some just like blue painter's tape on the bottom of my little light bulbs to help keep them in place here. And some folks will actually get a piece of cardboard or something like that and actually just physically use hot glue to glue these down in place. And then you don't have to worry about things sliding around, and students can still connect and disconnect things as they need to. I'm going to connect to graphical analysis so you can see what my current probe is reading. I'm going to disconnect this guy for now. And I'm going to go to graphical analysis here. And I'm going to search for my 2 current probes. I have one that's my test probe, and then I have a second one here that I'll use as to kind of do my investigation. So I'll connect to my first one and my second. By default, graphical analysis gives me a graph of current versus time. That's not really useful to me today because I don't expect the current to change real quickly. So what I want to see are the actual current, how much current is flowing. I'm going to turn off my graph, and I'm going to make the graphical analysis window much smaller here so that I just have my meters showing. There we go. And I'm going to make my window here. Okay. All right. So I'm going to connect my circuit here, and I can see that current 1, that's my test current ammeter. It's reading about 46 milliamps. And that's with all 3 bulbs here. And if I were a student, I might say to myself, okay, if I want to measure the current through this first bulb here, bulb 1, maybe I should, connect across it like I have, like these guys are. When I connect the current probe and this other wire to it, I use these terminals here. So maybe I'll do the same thing. Then I'm going to connect to here, and I'm going to connect here. And when I do that, whoa, wait a minute. I see that my bulb, the bulb I'm trying to measure, actually went out. And these two other bulbs actually got brighter. And I can see that the current changed, the current reading as well changed. You know, it's different than what it was before. I disconnect this and now it goes back to 45, 46 milliamps. So probably that was not the correct way to measure the current through this bulb. You know, maybe they say, oh, well, the current probe, the test current probe is connected to two different things. So maybe I should do the same. I should connect to two different things as well. And so I'm going to take and I'm going to measure, I'm going to take and connect to this side here, and I'm going to connect to this one here. Whoa, now this one's really bright. My test bulb is really bright, and my current is really high, and both these bulbs went out, right? Students can play. They can disconnect things, reconnect things as much as they want, and they're not going to burn out any of these bulbs. They're not going to blow the fuse on the current probe. And eventually, they'll get to the point where they realize, well, look, if I disconnect this connecting this alligator clip here and put my current probe in the same place that I was before, I end up with the same current as I had before. Both these are reading, both my current probes are reading the same thing. The brightness is the same. I got the same amount of current that I did before. So I must be measuring the current flowing out of this bulb. That's what we want them to understand. And we want them to see that depending on which way they connect their red and black leads of the current probe, they get a positive or a negative reading. And that positive or negative reading tells us which direction the current is flowing through the current probe. Right now, this current probe is reading negative, and that's because current is flowing through the black lead, backwards through the ammeter, and out the red lead. And so I get a negative reading there. We want students to see, like, connect that idea that there is a direction to the current and that these ammeters are designed to tell you that direction. We want them to understand that. I'm going to go, so let's go back to this. Things that you, like I said, there are, this is a great introduction to circuits because students can play without having, you don't have to worry about them, blowing things up, the smoke escaping. There aren't any real wrong answers. Everything that a student does can lead to some meaningful learning, like when the bulb goes out, you might ask, what happened there? Why isn't the bulb lit anymore? And hopefully they'll come to the conclusion that, well, that's because electricity isn't flowing through it. And it's like, well, why? Where did that electricity that was going fluid, where did it go? Likewise, if the bulb burns brighter, what does that tell us? Well, there must be more electricity flowing through it. Well, why is that? Well, if there isn't any flowing through this bulb here, then that means maybe there's more to flow through everywhere else. Anyway, these are the kinds of ideas and the kinds of questions that we want them to investigate. Once they have an understanding of how to use the current probe, they can move on to another activity where they look at the junction rule. I'm going to go back to my presentation here so we can talk a little bit about that activity. So when the junction rule is the idea that when you have a split, a place in your circuit where electricity can go one way or the other, that the current flowing into that junction must be equal to the sum of the currents flowing out of it, right? And the reason why this lab is called conservation of charge is because that's the idea that comes from it. The amount of charge that's flowing through it must be the same. And for this one, you might first show your students, if I have a single bulb and I connect a second bulb this way, you create a series circuit for them, then I can see, can see that the current decreases. Likewise, if I take a simple circuit with just a single bulb and I connect it this way and you connect it in parallel, then actually the amount of current increases, right? So then the question is, what happens if you have both series and parallel connections? Then this circuit here is an example like that. You might give them other circuit diagrams. You'll see that in the actual lab write-up that's in the folder, they have a couple of options there. They start with this one, and they have a couple of options, other things they can explore. But we want students to look at, now that they know how to measure the current through any one of these three resistors, we want them to do that, measure that current between the three, and then add them, and then look at those numbers. And ideally, they discover that, that the total, the current through resistor 2 and resistor 3 is equal to the current through resistor 1. This activity can be done with batteries and bulbs. It can also be done with resistors, just simple ordinary resistors. If you do it with, I would suggest that even if you're planning on your students using resistors, that you at least do the preliminary observation using bulbs. And that's because it's really easy to see with light bulbs that when the current is greater in a parallel circuit, the bulbs are lit more. And when the current is less in a series circuit, that the bulbs are dimmer. That's just much easier to show that way. But then when you have them do the actual the activity, whether they're using bulbs or resistors, it's most helpful if they all have the same resistance. And that's just because it's really obvious when R1 is when R2 and R3 are half of R1, it makes it easy to see like, oh, I've got all this current going through R1, and then it splits up equally between R2 and R3. The really quick students will realize that even if R2 and R3 are different, that the sum of those currents still add up to the current through R1. But when the resistors are the same, it's pretty obvious. I'm going to switch back and I'll rearrange my circuit here so it's the same way. So Carrie makes a good point there that these bulbs, we like to think that they're all identical. They won't be. And especially as they age, it tends to change a little bit too, but you do the best you can. Sometimes you end up having to do a little bit of hand waving. So what I'm going to do is I'm going to rearrange my circuit here so that I have the circuit that we had before, where we have R1, our resistor is just going to be, actually, maybe I'll leave this guy in here. I've got 2 current probes, so I might as well use them. I'm going to move this current probe so it's measuring the current through R1. Here's my R1. And then I have 2 options for the electricity to flow through. Well, it goes from R1 and it can go to R2 or R3. I'm going to use maybe I'll use the screen guy here. And then those go back to oh, that's the problem there. Those go back to the battery. I'm going to do this guy. I'm going to take this guy and connect it back here as well. What's going on? I don't know that you can see how dim these guys are. Those are really dim. But then I would use my current probe to measure the current through each of these guys. And I could do, just like before, I get some good readings about how those, that they add up together like that. The last activity takes advantage of the fact that we have these light bulb or these batteries have a plus and a minus on them. That's something that students are going to discover right away, especially if they're kind of playing around with things and they're building these circuits themselves. They might ask, what does that plus and minus mean? And up to this point, we haven't talked about voltage at all. And so this next activity is all about voltage and how that voltage changes throughout the circuit. Yeah, Fred makes a good point there about how the brightness it's proportional to the current, but it's not necessarily a linear proportionality. Like twice as bright doesn't necessarily mean twice the current. So this one, these particular battery holders that I am using today, they only connect together in plus to minus in the quote unquote correct orientation. So for this particular activity, you would need more alligator clips because you want to be able to flip them around and stuff. But the idea is that students are going to measure the voltage across each of the components in the circuit. They're just going to build a simple series circuit here with 3 batteries and 2 resistors or 2 light bulbs. You'll first show them that if I have a single battery and a single resistor or light bulb, that the voltage that the voltmeter measures is the same across both, and that one of them is positive and the other one is negative. And then you add in a second battery. So now I have 2 batteries. And if I measure the voltage across those 2 batteries, or each battery, that's still the sum of those 2 is equal to what I get across my resistor. Again, those 2 might be positive and this one might be negative. But then students are challenged to try different combinations. Let me show you what that might look like. So students are challenged to try different. This is Ohm's law. Here we are challenged to try different configurations of the batteries. What happens if I flip that positive and that negative? And they might try, so this is what they start with, but then they might try different combinations. Here, that's all positives. Here we have the middle one is flip-flopped. Here, the last 2 are flip-flopped. And again, they're measuring voltage around. And what we want to help lead them to is this idea that the positives add up to the negatives. That as you move around, all your ups have to equal all of your downs. One thing to note about this is in order to make that work out well, they need to decide that on a particular orientation. How are they going to use the voltage probe? And so you might suggest something like, as you move around the circuit, the red lead is always ahead of the black lead. Like you imagine as it moves around this circuit, if I'm measuring R1, that my red lead would be ahead of the black lead, and then when I move to R2, the red lead stays ahead of the black lead. So that way you always have a common convention for your, or I should say your measurements follow the same convention. That way all your positives end up adding to all of your negatives. And it works out the way you expect it to. All right, the last part is Ohm's law. Ohm's law, this is probably, already got an Ohm's law activity. And like I said, you can insert Ohm's law at a lot of different places along the sequence. Once they know how to measure current, if you want to bring in the idea of voltage, earlier, you can do that. I like to do it at the very end because it's a great way to tie together these 2 quantities that students now know how to measure, and they have some idea of how those quantities vary. And Ohm's law kind of connects the 2 together. Well, our Ohm's law activity actually, rather than using batteries, uses a variable power supply, something like a benchtop power supply where you can dial in how much voltage you want. And students end up plotting voltage versus current. And the resistance shows up then as the slope of that curve. And you start off with 2 resistors. They has them do like a 10 ohm resistor and a 50 ohm resistor. And you can see the slope of those 2 voltage versus current curves are very different. And then they had the students compare it to a light bulb, like the light bulbs that we're using here today. And that is interesting because it doesn't follow Ohm's law very, if at the very small currents it works fine, but then once it starts shining brightly, you end up with a much different sort of thing. You can see in the instructor notes for that Ohm's law lesson, you can see that the data works out pretty well. Here's our 10 amp one, our 50 ohm one, much higher, greater slope. For a light bulb, you find that at the beginning, the potential is pretty low for the voltage, and then as it increases, rather than being a straight line, it works almost into a parabola there. That's real interesting, especially for if students if this is their 2nd year of physics, to move beyond just your simple Ohm's law relationship. That's the kind of sequence that I recommend. Like I mentioned before, These work well with the batteries and bulbs. You can also do these same activities with the Vernier circuit board. The biggest difference with the circuit board is in this third activity, when you have multiple batteries, you actually have to pick the batteries up out of their battery holders and flip them around the opposite way. Fred asked a question a little bit about seeing lots of fluctuations with their power supply when they do Ohm's law. One thing I didn't mention before about this Ohm's law experiment is when you put a variable power supply in front of your students like that, their impulse is to turn that knob all the way up. And while that's really fun, that's where you end up with burnt out bulbs and that sort of thing. And so if your power supply has a current limit on it, and you know what kinds of bulbs and resistors your students are going to be using, choose a good current limit on that and make sure that's set, and then tape it into position so students can't change that. That'll spare you a little bit of grief later on when they're burning out lots of bulbs. Fred, for you, as far as yours, I'm not sure. We'd have to look into it a little bit more. I'll make a note to send you an email and follow up with you about it. But there are a couple of things that might be happening there, why you might see such fluctuations in the measured current. All right. Well, I don't know, I think I got everyone's questions. If you have any additional questions, I'm happy to answer them. Otherwise, we'll save this recording, and it'll be posted on the website here in a week or so. You'll get an email with a follow-up. We appreciate your attending today. And please, if you have questions, feel free to reach out. We are happy to help. We want to make sure that you make the most of the Vernier products that you use. Dylan's posted a feedback form in the chat. Please let us know how it's going. Thanks.
All right. Well, if anyone has any questions, yeah, please reach out. We are available. Visit our website. There's a contact us page, and you can shoot us an email. So we'll be available. All right.
Thank you.
Bye, y'all.